Right, good evening to all, and this live session is in continuation with the previous live session on the basics of casting. In the previous live session, we focused upon or we studied about the solidification process in a casting, how the casting solidifies, what are the different microstructures, and the different grain forms that uh, develop during the solidification process. Now, in this session, I will be looking at the flow analysis of how a molten metal flows inside the mold cavity or the mold and what all factors govern it. Okay. Before we do that, let us quickly draw a simple casting, okay, with some basic components in this. So we'll just brush up the basics. We all know this. For those who don't know or who have forgotten, it will be quite useful. Okay, so this is the casting and this is the parting line, which is dividing the mold into two parts. The upper half is called cope, the lower half is called drag. Okay, and let me draw the components inside. All right, and then one by one we'll start discussing them. There might be some points which will be left, so do not panic. Okay, just type it in the chat box. After the explanation is over, I'll see that I'll tell you about them as well, but participate in the lecture before we go on to the question answer session. Okay, now this is basic casting, the cross section. So this is the cope. Okay, this is the molding sand, the red part. Okay, now this portion, what do we call this? This is known as the pouring basin. So you take your molten metal and you bring your ladle on top of this pouring basin and you pour the molten metal into this. It collects over here and then it runs down this channel, which we call sprue. Okay, this taper section is known as sprue. Everybody is familiar with this word sprue. Okay, and then as the molten metal flows down this corridor, the tapering corridor, which we call sprue, it now collects at the bottom. This little this little reservoir or this little pool is known as sprue well. This is sprue well. The function of sprue well is to act as a reservoir for molten metals before it flows down the to the cavity. Now, okay. Now, once the molten metal is collected over here, it slowly starts its journey towards the mold cavity. This pathway, or this channel, is known as your runner. So this is the channel through which your molten metal flows. It's a cylindrical section. Okay. People who have come in late, please make sure your audio controls are disabled so that I don't have to go back and forth. Right, now then you come to a section like this. This section is known as skim bob. Skim bob. Now skim bob is basically a part in the casting section to trap the impurities. So the molten metal will have some impurities in it, okay, due to the furnace in which it melts or due to the ladle in which it is taken, and when it is poured in the pouring basin, as it flows down, these walls are made up of sand. So when the molten metal comes into contact with these walls, the sand is porous, so the porosity matters. If it is very porous, if it is very permeable, okay, some sand will come into the molten metal and will be a part of the casting if you do not remove those impurities. So that removal of impurities is carried out via skim bob. In skim bob, so I'll write down the function as well. It traps impurities. So in skim bob, you are basically uh, clearing heavy impurities also and light impurities also. If the impurities are heavy, they will settle down at the bottom, and if the heavy as compared to the molten metal, heavy means the density is high, okay, and if the density of the impurity is less than that of the molten metal, it will be floating at the top, and the pure molten metal will continue along the runner. Now you are going up from the runner, and then suddenly there is a drop in the cross section area. What is this section called? Anybody? Can anybody tell me what is the name of this section? No, Piyush, that is not in-gate. Anybody? Can anybody tell me the name of this section where the cross section of the runner is decreasing? Others? Come on, anybody? No. Just a minute. See, I've told you, people who are arriving late, please disable your audio controls. Okay. See, this part is called choke. A choke is a place where the cross section area of the runner decreases, or you can say this is a point or a section, preferably a section with minimum cross section area. Now why are you decreasing the area before you reach this is the mold cavity, okay, this is the mold cavity. Now before you reach the mold cavity, you want that your liquid velocity or your fluid velocity should reduce. So you put a minimum cross section area over here and it reduces the velocity. Okay, now with the reduction in velocity, what happens? There is a reduced turbulence, the Reynolds number drops. As the Reynolds number drops, the turbulence in the flow is controlled. Because if you have high turbulence and that high turbulence liquid molten metal is entering the mold cavity, it will cause a lot of agitation inside the mold cavity. It will cause a lot of turbulence inside the mold cavity, and it will also cause erosion at the mold cavity walls, which will trap sand particles inside the liquid molten metal, and when it solidifies, it will not be a pure solidification. So you have to reduce the flow, or you have to reduce the flow velocity of the molten metal, and then see no, you have minimum cross section area over here, okay, and then it increases. You are actually controlling the flow. Okay, you're controlling the flow rate. Okay, your flow rate is controlled, so you allow the metal to flow in a controlled manner. Okay, the velocity is not increased, it is maximum at this section, but when it comes out of this section it decreases again because the cross section area increases. It is minimum at this section. Okay, and at this section the main focus is to control the flow. So you kind of resist the flow at this section, and when it comes out it has a lower velocity as compared to what it has at this section. So this is the basic idea. Now your molten metal again flows through this runner passage. Now this section, which is just at the entrance to the mold cavity, these are called your gates. Okay, so these are called your gates. Now what is the function of gate? The function of gate is to allow the molten metal to enter the mold cavity. This is just a name given to a section. Gate is something through which you enter. Okay, so gate is a section through which the molten metal enters the mold cavity, right? After filling the mold cavity, okay, molten metal then goes in this direction and comes up through this. Now this part is called your riser. Now riser has many functions. I told you when your liquid metal solidifies, it shrinks. When it shrinks, it will be decreasing in volume. So when the volume decreases, you need reinforcement metal to fill up the lost space. So that reinforcement metal will be supplied through the riser. This means riser acts as a reservoir to compensate for solidification shrinkage. Okay, so this is one of the most important functions of a riser. Okay, that it acts as a molten metal reservoir to compensate for solidification shrinkage. The second practical application for a riser is, for example, it is not you don't have a riser, you don't have an opening on the other side of the boring basin. Now how will you come to know whether your cavity has been completely filled by the molten metal? You will never know it. So when the molten metal rises and comes out from this riser, you would come to know that yes, your cavity inside has been completely filled by the molten metal. Okay, so these are some basic parts of a casting. Now we'll move ahead. We'll move ahead to a more not very common term. What do you understand by hotspots? What are the hotspots in a casting? These are some questions which might crop up directly in your exam. Okay, and you should know it because these things are not very commonly given in books. Okay, so what do you understand by the term hotspots? Anybody? Vijay Sampath, can you tell me what you understand by hotspots? And or Ravi Kantharaman? Anybody? Others? Kuntal, anybody can tell me what you understand by hotspots? The rate of decrease of temperature is high. No. See, hotspots are those points in the casting which will freeze at the last. Okay, so these are points in the casting, or these are sections of the casting. We'll come to this when we study riser design. Okay, these are the points in the casting which freeze at last. This means the heat loss from these spots is the least. They will freeze at last. Okay, now there is an important thing that you should note down at this moment, that you will understand it when we start the riser design topic, is that hotspots, okay, should be fed, just note it down, they should be fed up to the last moment. They should be fed up to the last moment till casting is completely solidified. Okay, so this is a condition that is applied on hotspots, that they should be continuously fed by molten metal. Okay, because these are the things which are you know, solidifying at the last. Why? We'll come to that when we study the riser design, and this is in correlation with the solidification process. The solidification starts from the outer walls of the mold towards the center. Okay, so we'll come to that when we do that. Just remember this for the moment. Okay. Now there are some other points also to note. Okay, these points are, let us note these down in your notebook. So when we are doing the topics later on, you will be able to recall them. Okay, so location of riser should be such that it ensures directional solidification. Okay, so you have a particular direction in which solidification proceeds. There you should locate your riser. Okay, note it down. Next point, the heaviest section. These points are not in your notes, note them down. The heaviest section solidifies at the last. The heaviest section solidifies at the last, so riser should be so located to feed them. Okay, now if you correlate this point with the condition for hotspots, you would start getting a little bit of idea what I'm talking about. Okay, so heaviest sections are basically your hotspots. They solidify at the last. Okay, now let's move on to something which we call sprue. Okay, now before we go on to sprue, I would like to tell you that the flow inside a casting, or the flow inside a mold, basically, it is governed by two principles. What are those two principles? Anybody can tell me. Two principles governing flow inside a mold. Flow of molten metal in a mold cavity, or in a mold basically. Yes, one is Bernoulli theorem. Okay, and the second one is not gravitational, it is continuity theorem. The continuity principle, keeping the flow rate same across all sections so that the cavities inside the mold are completely filled by the molten metal. Okay, so these two principles govern the flow of molten metal inside the mold cavity. If you, let us say, if you want to recall Bernoulli's theorem, it is something like this. If you apply Bernoulli's theorem at two sections, it will be P1 plus H1 is equal to P2 plus V2 square by 2G plus H2 plus F. Okay, so P1, P2, these are pressure values, pressure heads. V1 square by 2G, V2 square by 2G are your kinetic heads or velocity heads, and these two are your static heads, H1 and H2, or datum heads, and this is your frictional losses through the section. Okay, now continuity theorem is easy. Q is equal to A1 V1 is equal to A2 V2. This is your continuity principle. Okay, now let's start the designing or the studying the shape profile for a sprue. Okay, let's now study about some basic concepts for sprue. We all know sprue is located below the pouring basin. Now pouring basin is a kind of a it's kind of a cavity in which you pour your molten metal. It collects there as a pool and it slowly trickles down the sprue, fills up the sprue well, and then goes across the runner to fill the mold cavity. Now sprue profile is never cylindrical. It is never cylindrical. Okay, and it is always tapering towards the bottom. Okay, so this is a condition for sprue. It should never be cylindrical. Okay, why it should never be cylindrical? This I'll tell you, but the mathematical calculation will be your task. I will do the mathematical calculation for the tapering bottom. Okay, now let's start. Let's make a sprue to analyze what I am talking about. That what is the tapering section? Let's make a sprue. Let's draw a center line. Okay, right. Okay, and let me draw three sections. Let me draw, this is my first section, section 1. This is my second section, section 2, and this is my section number 3. Okay, this is a sprue, right? And this part is your pouring basin. Everybody is understanding? The newcomers, are you people following what I'm saying? Yes or no? Okay, now section 1. Section 1 denotes the free surface of molten metal. So this is the free surface of molten metal, right? Number 2 is the sprue top. Number 2 is the sprue top. This is the top of the sprue. Okay, and number 3 is the sprue bottom. Okay, that is the bottom of the sprue, this section. All right, let me say this is my reference line, section number 3, datum, and let me take this height as HT and this height as HC. This is the cup height, okay, and this is the total height. Okay, now let us apply Bernoulli's theorem between section 1 and section 3. Okay, the assumption, okay, let me move on to another page. So just remember this. Let me copy it on the next page. The slide has finished. Abhinav, HC is the cup height, the height of the pouring basin cup. Okay, so, right, we have the picture over here. HC is the pouring basin cup height. Okay, now let us apply Bernoulli's theorem between section number 1 and section number 3. Okay, and when you are applying this, there are two assumptions that you need to take into account. Basically, three assumptions. First assumption is that entire sprue is at atmospheric pressure. Okay, so entire sprue is at atmospheric pressure. This means the pressure at P1, the pressure at section 1 will be equal to pressure at section 3. Okay, this is one assumption that you do. Second assumption is that the velocity at section 1 is 0. The molten metal has no velocity whatsoever. And the third one is there are no friction losses. That is F is equal to 0. Okay, and let us apply the Bernoulli's theorem. For section 1 it will be P1, okay, plus V1 square by 2G plus H1 is equal to P3 plus V3 square by 2G plus H3. Okay, now if you look at it, P1 and P3 they are cancelled off. V1 is 0, so it is not existing. The value for H1 is HT because you are measuring from the datum plane, that is your reference section number 3. So section 1 is at a height of HT. So H1 becomes HT. So this becomes HT. Okay, you will have V3 square by 2G plus, what is the value for H3? H3 is, section 3 is at the datum plane, so the value for H3 is 0. Okay, so this becomes 0. From this equation I can calculate that V3 is nothing but 2G into total height. So this is one relation that you get. Understood or no? Okay, yes, it's 0. Now let's come to the application of Bernoulli's theorem between section 2 and section 3. Okay, so when you apply Bernoulli's theorem between section 2 and section 3, you will get P2 plus V2 square by 2G plus H2 is equal to P3 plus V3 square by 2G plus H3. Okay, right. In this again we will be assuming just a minute. Oh, sorry, this is not between P2 and P3. This will be between P1 and P2. So we will not take 3 into account. It will be P1 and P2. So this would be P1, V1 and H1. Okay, and on the other side you'll have P2, V2 and H2. The assumption over here is the same, that V1 is equal to 0. Okay, this one, and over here also P1 is equal to P2. So P1, P2 gets cancelled off. V1 is already 0, so it will no longer be existing. The value for H1 we know is HT. The value for H2, if you go to the diagram, H2 is what? H2 is this height. This is H2, which is H2 is HT minus HC. Okay, so H2 is HT minus HC. So H2 will be HT minus HC. That means that the thing is saying that it is not P, it is P by rho G. It will be cancelled off, because here also you will have rho at the bottom. Here also you will have the specific weight at the bottom. They will all be cancelled off. Okay, so it is just for an analysis purpose. We are not we know what this is. This is a pressure head. Okay, so pressure head is pressure value upon the specific weight. Okay, so H2 is Ht minus Hc. So if you plug in the value over here, you would get V2 square by 2G plus Ht minus Hc, and this H1 is nothing but Ht. Now Ht and Ht are cancelled off. So from here I will say that V2 is equal to root 2GHc. So we have got the value for V3 and we have got the value for V2. If you apply continuity principle, okay, between the sprue sections are 2 and 3. 2 is sprue top, 3 is sprue bottom. So it will be A2 V2 is equal to A3 V3, because the flow should not be disrupted when it is flowing through the sprue. Okay. Now A2 into root 2 GHc is equal to A3 into root 2 GHT. Root 2G cancelled off. This means it will give us A3 by A2. This is equal to V2 by V3, and this will give me under root HC by HT. So this is the relation between the cross-section area and the height, which tells us, if you look at it, area is proportional to root h, or you can say h is proportional to area square. So your area is varying parabolically as you decrease the height. Okay, so this is what is happening. As your height changes, your area changes parabolically. So in actual or in theoretical sense, this is not a straight line. This is basically a line like this. Okay, but for the sake of calculations and for the sake of representation, this is shown with a straight line. Okay, so with the variation of height, or with the area, okay, the area changes parabolically. This is the configuration of a sprue, or how a sprue should be. I hope this is clear to you. So with this, the sprue should always be of a taper section. It should not be cylindrical. It should not be cylindrical. Why? It should not be cylindrical. Why it should not be cylindrical? Can you analyze it? See, whatever the variation of the dimension is, the main concern over here is that the section is parabolic, it is not straight. Why it is not straight? I told you. Abhinav is asking why pressure head at 1 and 3 are same. Where are our assumptions? This is the assumption. This is the assumption that the pressure at all the points 1, 2 and 3, they are same. They are all atmospheric pressures. So 1 and 3 will be same. So as 1 and 2. The pressure at all sections is same, because we are assuming that there are no friction losses, there are no turbulence, there are no pressure variations. within the flow of the molten metal. Okay, so this is an assumption that you make. Now, if you create a cylindrical sprue, I leave it up to you. Draw these three sections, okay, and perform the same analysis that we did. Okay, now you will come to a conclusion that when you have a straight profile of the sprue, there will be some flow disruptions. Flow disruptions means that within these three sections, yes, that is what I am coming to. Within these three sections, there will be a negative pressure head at one of them. Which one of them? I leave it to you to find out. I'm just giving you a hint. The analysis has been just presented to you. Take between 1 and 3, and then between 1 and 2, and then analyze. At a particular section, it may be 2 or it may be 3. Find it out. You'll get a negative pressure head. Negative pressure head means induction of air inside. When air is trapped within a flowing liquid, the flow is disrupted, or your flow is no longer continuous, or your flow rate is affected. Okay, so this induction of air inside this molten metal due to a creation of a negative pressure head, this is known as aspiration effect. Okay, now due to this aspiration effect, okay, we do not use cylindrical sprue shapes because they disrupt the flow. Now, if you look at it practically also, you don't need to be a mathematical genius. See, if you start pouring your liquid through this, what will happen? It will fall freely. It will fall freely. Once it falls freely, uh, at this section you will start getting very high flows. There will be some eddy current formation at this section, and there will be some flow disruption at this. So you'll have I'm just giving you a hint, you'll have a negative pressure head at section 2. You will have air inclusions at section 2, which will not allow it to flow further. But instead of a cylindrical thing, if you create a tapering section, so what will happen? When you pour in the liquid, it will start filling up like this, and it will push out any air from it. Okay, and then slowly it will trickle down into the sprue well and then onto the runner. So this is the practical thing, that with the tapering section the flow rate is also controlled, and with a cylindrical section it falls freely, creating a negative pressure head at section 2, which is called an aspiration effect. Understood or no? Now if you look at, this was about sprue. If you look at another section or another component within the mold cavity or within the mold, which was gate. Okay, now gate is the point of entry of molten metal into the mold cavity. Okay, now gates are of 4 types, but we'll look at only 2 types of gate. The first type of gate we'll look at will be a top gate. The second type of gate we'll be looking at is bottom gate, because these 2 gates are quite important from the examination point of view. Okay, you will look at top gate and we'll look at bottom gate. Okay, let us start our analysis by analyzing bottom gate first. Then we'll come to the top gate. So let us first draw what the top gate looks like. Okay, let me draw a bottom gate. Sorry, a bottom gate looks like. Let me draw a bottom gate. And when I'm speaking, write down these points as well, because they will help you recall some basic things. Yes, Niketan. So this is your sprue. Sorry, this is your sprue. This is your mold. Okay. Okay. So yeah, this is your bottom gate. So this is your pouring basin, this is your sprue, this is your runner, and this is your bottom gate. This is your bottom gate, and this is your mold. If you look at this, this will be the area of the mold. This thing is the total height of the mold. Okay, and this is the height of the filled cavity at any time. Okay, it takes some time to fill up, and let us say during any intermediate time you have a mold cavity height of h. Okay, now there are some very important aspects to a bottom gate. As you can see, with bottom gate, the molten metal is entering the mold from the bottom. Okay, so when it is coming from the bottom, it forces the air up and out of the mold. So there is no air entrapment in the mold. One thing. Second, it is reducing splashing and erosion of the cavity walls. So when your metal falls from the top, it will hit the bottom. When it hits the bottom, it erodes some part of the mold cavity wall, and also there'll be some splashes, okay, which will create some more trouble. So in this, there is no such problem, as it enters at the bottom and slowly it starts filling up the mold cavity. Okay, now bottom gate actually involves longer filling time. The filling time for a mold cavity with the help of a bottom gate is quite long. Okay, this is preferred for steel castings. So you should note these things down. Okay, so you have longer filling times, reduced splashing and erosion of the mold cavity walls, longer filling time, and is preferred for steel castings. Okay, now if you look at it, let's dimension it. Let us say this is your total height. Okay, and this is the bottom gate. So this will be the area of gate. This is the area of gate. Now what we intend to do is we will find out the formula for the time taken up to fill a mold cavity with the help of a bottom gate. Okay, so this is a straight away question in the gate exam on the casting topic. Before I do that, I'll take a 5-minute break. I'll go and have a glass of water. My throat is drying up. So anybody wants to take a break for 5 minutes, go ahead. We'll meet after 5 minutes. Okay. Okay, let's resume the session. Abhinav, H is the mold cavity height at any time. Okay. We need that the mold should be completely filled. That is, it should be filled up to this height. But at any intermediate time, it is only filled up to height H, let us say. Okay, so we are uh, looking at it in that context. Okay, understood or no? Great. Now let us move on. Now we know. Okay, again a problem. The slide has finished. I'll have to copy this onto another page. Great. Now we know that the application of uh, continuity principle will say that the flow rate through gate is equal to flow rate going inside the mold, isn't it? Now, let us say that you starting your clock at t is equal to 0. Okay, let us say start t equal to 0. Now, let us say after time tt, let the mold fills up by dh. Okay, so in time dt, the mold cavity is filled up through a height dh. Okay, now what is the volume of metal in mold cavity after dt? So the volume of metal in the mold cavity is area of mold into the height up to which mold cavity is filled in that time, that is dh. So area into dh. Moving ahead, what is the flow, not flow rate, what is the flow through gate in time dt? So that will be flow rate, that is area of gate into velocity of gate, or velocity through gate into the time. So this gives you the meter cube value, not meter cube per second. Okay, now moving ahead, see h is the mold fill height at any instant. So at any instant of time your mold will be filled up to height h, let us say. Okay, now we have to take, if you go into the diagram again, let me extend this level, okay. So this is the level I'm interested in, and this is section 1 and this is section 2, up to which the mold cavity is filled. Okay, now I will apply Bernoulli's theorem between these two sections at 1 and 2. Okay, I know the datum is this line, so section 1 is at a height ht, okay, and section 2 is at a height h, so this is h, right? So let me go back to my calculation. You will have p1 plus v1 square by 2e plus h1. So h1 is ht, and this will be p2 plus v2 square by 2g plus h. Okay, now we know that throughout the pressure is same, so p1 is equal to p2, all atmospheric pressure. Okay, the velocity at the top of the molten metal, that is at the top of the boring basin, is 0. So V1 is gone. So P1 is equal to P2 and V1 is 0. Okay, now the velocity 2 is the velocity of gate. Okay, the velocity through which your molten metal is rising in the cavity is the velocity of liquid coming through gate. So this is V gate. So if you look at it, or if you substitute it, ht is equal to vg square or v gate square by 2g plus h. From this equation I can say that velocity of gate is root 2g ht minus h. Okay, so this is a formula to calculate the velocity of liquid through bottom gate, okay, at any instant with height h. Now let us substitute this value. Let us first of all equate this value, that is the volume of metal inside the cavity after, okay, and let us equate this. These two values have to be equated as per the continuity principle. Okay, we see the only point of entry inside the mold cavity is the gate. Okay, so through gate there is some liquid flowing in and the metal is rising up. Okay, so what is V2? V2 is basically, this is the section 2. So what is the velocity of liquid at this section? This is basically the velocity of liquid coming through gate. So it is rising at whatever velocity your liquid is entering. Okay, because there is no other restriction. This is why V2 is equal to V gate. Now let's move ahead. Now let us equate the volume of metal in the mold cavity after time dt and the flow through gate, because the flow through gate in that time will be equal to the volume inside the mold cavity. So A mold into dH is equal to AgVg dt. Let us equate them. So you will have Ag, A gate into V gate into dt. This is equal to A mold into dH. So this is the value that you will get. Substitute this value over here. So you would get A gate into root 2g ht minus h into dt is equal to A mold into dH. Okay, let me rearrange this and you would get dt is equal to A mold upon A gate, okay, into root 2g and you will have dH upon root ht minus h. This is what you will have. Now your time starts from t is equal to 0 to tf, that is the total filling time. Okay, and your height starts from h is equal to 0 to mold height, that is h mold. So when you integrate this part or this equation, you get that tf is equal to 2A mold. I hope you all know how to integrate, so I am not going into that detail now, into root ht minus root ht minus h mold. Note this formula down. This is not in your notes. So this is the time taken by a bottom gate to completely fill the mold cavity. Okay, so note this down before I move on. When you have noted it down, I'll move ahead. HT is the total height, and H mold is the height of the mold cavity. I hope you have understood this part. This is quite clear. This is very easy, isn't it? Great. Let us move ahead. Let's now come to top gate. Uh, Top gate, as the name implies, will have molten metal coming in from the top. So your uh, cavity would be like this. Okay. So this is the pouring basin, this is the sprue, okay, and this is the gate. So directly your molten metal flows inside this mold cavity. So this is the mold, okay. This is the area of the mold, and this is the height of the mold. This thing is your gate. This is the area of gate, okay, and this is the value HT. Okay, now top gate in this configuration will act as a riser too. Okay, it will act as a riser as well. Now what happens is, when the mold is completely filled, the solidification will start from the bottom up. So the solidification will start at the bottom and will move upwards. Okay, in this you will have high turbulence and therefore high erosion. Okay, and this is used for castings which have simple design and are big in size, and preferably it is used for grey cast iron. Okay, now this kind of a gate configuration, that is top gate, note this point down, this is not preferred for non-ferrous metals. Okay, so this is not preferred for non-ferrous metals. Why it is so? Because see, it has a lot of turbulence associated with it, and with high turbulence there is a considerable amount of dross formation. Now what is dross formation? Dross formation is basically your white scum, white foam that is collected on the top of the uh, molten liquid because of impurities associated with it and the air inclusion due to heavy turbulence. Okay, so this is the reason it is not preferred for non-ferrous metals. Okay, right. Now let us it is comparatively less. It is not that it will never form, it is comparatively less as compared to in the non-ferrous metals. Right. See, the velocity of liquid through gate, the velocity through gate will be root 2 GHT. Okay, this will be the velocity through gate. Now, if we have to find out the time taken to fill a mold cavity with the help of top gate, it will be equal to volume of mold divided by area of gate into velocity at gate section. So the volume of mold is area of mold into height of mold divided by area of gate into velocity of gate. So the only thing that you need to calculate is velocity of gate, whose value is root 2 g ht. Okay, so this is what you get from top gate. Okay, now the last part of this topic is your riser design, and as I can see from my watch, I would not be able to start off with the mechanics of machining, so we will do it in the next video session. The last portion of this lecture would be riser design. Now, we know what a riser is. Okay, so the first is it allows for visual check whether the mold cavity has been completely filled or not. So it provides for a visual check. Okay, then it pushes out air from the mold cavity. It pushes out any entrapped gases if you have inside it. Okay, now, and the last important part is it compensates for solidification shrinkage. It compensates for solidification shrinkage as it acts as a reservoir for molten metals. Okay, now there are some points you should note down. I'll keep on writing them on the board. Is that if no riser is provided, okay, if no riser is provided, solidification will start from the outer walls to the inner walls, also to the inner of the mold cavity. So solidification starts from outer wall to inside of the mold cavity. Now what is happening when this is happening? So this is the mold cavity. Okay, we studied in the last section, you have a film formation, chill zone. This is the chill zone, and it proceeds from outside to inside. So this is what happens. Very quickly, this part, the green part, shows that the liquid has been solidified. This is in case of no riser. Okay, and the inside of the cavity will still be liquid. Okay, now what happens? See, as it cools down, as this mold, this casting is left to cool down. Okay, Niketan, this was discussed in the last lecture. If you were not present, go through that lecture and then we'll take up your doubts. Right? This is a link to dendritic growth if you listen to that lecture. Okay, so as I told you, if you have no riser, cooling will start at the chill zone and will proceed towards the inside of the mold cavity. Very soon, this much part would have solidified, and the inner part will still be a liquid. Now what is happening? You're still allowing it to cool down. The casting is cooling down up to the room temperature. Now, when this liquid part cools down, okay, this liquid part will shrink, and when the shrinkage occurs inside this portion, there will be some voids that will be created, because when shrinkage happens, the volume decreases, and the riser compensates by providing extra molten metal in that portion where shrinkage has occurred. So in this, the shrinkage will occur. There will be no compensation from the riser because there is no riser. Okay, so as this liquid shrinks, it will leave some voids. Okay, so this is a defect in the casting. We all know that the casting is porous. It has voids inside which has low strength. So a riser, this means, is a mandatory requirement for any mold setup or any casting setup. Understood? Now, moving ahead. A riser should be large enough to solidify at last. It should be so large that it solidifies at the last, because if it solidifies before the casting, there is no point of using it as a reservoir to compensate. Okay, so it should solidify at the last. Okay, and should be capable of holding molten metal to be used for shrinkage compensation. Okay, so the main point in this is to tell you that it should solidify at last, not before the casting in any sense whatsoever. Now, next point. Cylindrical risers are the best, okay, because they lose heat very slowly. So, if they lose heat very slowly, this means, see, it is not a question of may, it should never solidify first. Because if it solidifies first, the whole point of using a riser is not met. Okay, so this, in this point, it says that it should lose heat very slowly. Okay, so heat very slowly means the rate of decrease of temperature inside the riser should be very less. It should stay liquid for as long as it can, so that as the casting freezes, the compensation can be done. Okay, so for this purpose, cylindrical shape is the best to use, as they lose heat very slowly. Now, what are the factors that govern this thing? I'll just tell you after one more point. Okay, now a riser is designed with minimum possible volume, so it should have minimum volume. Okay, because we need maximum volume for the mold cavity. Okay, it should have the minimum possible volume with cooling rate slower than the casting. It should solidify at the last. A point, a numerical value that you should note, this is a empirical value. The volume of riser, how much volume of metal should be in the riser, should be at least 3 times the shrinkage volume of the metal or of casting. So you know how much your casting will shrink. Okay, so 3 times that should be your volume of the riser. Okay, now if you want to increase the riser efficiency, so in a way, if you look at it, a riser should be able to withhold heat within itself for a very long amount of time. This means heat dissipation through the riser should be the least. Okay, this means riser efficiency can be increased by, first point, we can use insulating covers. You can use insulating covers around the riser walls, and these can be made up of POP. So what happens when this insulating cover comes into contact with the molten metal? It burns. It converts into ash. Now this ash provides insulation. Okay, so this means heat is kept inside the riser and it is not dissipated, thus reducing the uh, cooling rate. Okay, second, we use some exothermic mixtures, okay, to supply extra heat. So the main focus in riser efficiency is to contain as much heat as possible within the riser volume. Okay, now let us look at a formula with the help of which we calculate solidification time. Solidification time for a casting can be calculated by, or solidification time is proportional to this ratio, V by A square. Okay, now what is volume? Oh sorry, what is V? V is volume. Okay, and what is A? A is surface area. And there are two very important significance of these two terms, is that volume denotes the amount of heat stored, the quantity of heat stored within a volume or within a shape, within a body, how much heat is there. And surface area denotes the rate of heat transfer. So if you have high surface area, your heat transfer would be high. Okay, if your volume is high, your amount of heat will be high. This means that your solidification time depends upon directly with how much heat you have, okay, and inversely proportional to the surface area. Okay, so this is these are two factors which govern the solidification time. Now this is known as, the name of this is Chwovi, okay, wrong spelling, Chvorinov's rule. A Chvorinov's rule, if you equate it, there will be a C, a constant coming in picture. So this constant is your mold constant. This mold constant has a unique value depending upon the geometry of the mold, the mold properties, the kind of sand you are using, things like that. So it will be given to you, it will be given value to you. So with the help of this you can calculate the solidification time. Okay, now this was little bit about the casting that I wanted to tell you. Now if you can combine this with your notes, you will be at a much better position to actually attempt the gate questions on casting. Okay, so before I finish off, I would like to give you a task. Okay, yes, let us write down a question. It's very simple. If you find out the answer, just put it on the forum. Okay, now you need to find out There are three kind of castings given to you. First is you have a spherical casting. You have a spherical casting of diameter 20 mm. Second, you have a cylindrical casting. Okay, with diameter is equal to height is equal to 20 mm. The third one is a cube of side 20 mm. So these are the three kinds of casting you have with the given dimensions. You need to find out which of these castings have the least value of solidification time, or in other words, which freezes before the which freezes in the least amount of time. So this is the question that you need to look at. It's quite easy, just apply the Joy-Rho rules and you'll be able to find it out. If you find it out, put it on the forum and we'll look at it. So I will look at the worksheet answers tomorrow and we'll have the feedback by tomorrow evening. For those who have not submitted it, do so at the earliest, and that is by tomorrow afternoon. Okay, I'll be waiting for them in my email. And the next video lecture will be on the topic of we'll be starting the mechanics of machining. Okay, Avinav, C is a mold constant which depends upon the kind of mold you're using, the sand which you're using. So it will be given to you. It's a value which is given to you. It's an empirical value. Okay, yeah, that's what I'm telling you. Value for C will be given to you. It depends upon the kind of mold, the kind of sand you're using for the mold. That, okay, will be a given value to you. Okay, you're asking for this question. Just keep it C. Compare it by keeping it C. Okay, you can compare it with a constant value. It'll cancel off, and then you can see which one is giving you the least amount of time for solidification. Okay, so I hope you understood the lecture today. Okay, somebody is asking, I will very quickly repeat the shrinkage condition for no riser condition C. For those who didn't understand, let me put 5 minutes more on this. See what is happening. I don't know who indicate. Okay, see. You have no riser in this case. Okay, you have no riser. And when you put liquid metal inside a mold, let us say this is your mold. Okay, the moment the liquid metal is inside the mold, it freezes instantly at the cavity walls. Okay, so the freezing starts from outside to the inside. Okay, so the inner core of the cavity is still liquid, and after some time this core is surrounded by a very thick sheet of solid. This is completely frozen. Okay, and the inner core is still liquid. Now what happens, your casting is still being cooled down, it is still cooling down to the ambient temperature. So what will happen, when this liquid starts to cool down, it will shrink, but obviously, so when it shrinks, the shrinkage compensation has to be there, but there is nothing to compensate, there is no riser. So who will compensate for this? And it is surrounded by, solid from all sides. So it cannot have extra liquid metal to compensate for the shrinking. So when it solidifies, for example, this is the volume of liquid. When it solidifies, the volume reduces. and there is a void left inside the cavity. Now this void is not filled with the liquid and is, and as it is, this is a void inside the, this is an empty space inside the casting. With an empty space inside the casting, the strength will reduce, okay, and will affect other mechanical properties as well. So this is a defect in the casting. So no riser, okay, understood. So you need to have a riser in order to have proper solidification inside the casting or inside the mold cavity. Okay. When you have riser, you have a uniform directional solidification, that is from outside walls to inside walls. Okay, and it is, there's some question over here. The others is asking, if riser is present, then what is the pattern of solidification in top and bottom gate? See, in bottom gate, if you go to the diagram, let me go to the diagram. Okay, let's say this is the top gate. Now in top gate, it starts solidifying at the bottom, okay, and you keep on pouring it from the top, and as it keeps on filling the mold cavity, it will start solidification at the bottom. Okay, in case of bottom gate, again it will start solidifying at the top, because there is heat coming in from the bottom. Okay, so as you go up, it will lose heat much more rapidly as compared to the heat loss at the bottom, because heat at the bottom, you are having a constant supply of warm or hot liquid metal. So in this you will have from top to bottom, and in top gate you will have from bottom to top. Okay, so I hope this is clear to you. Next video will be, or next live session will be on the topic of machining. We'll look at some important factors which govern the machining process. So till then, have a look at this video again. I will provide you people with the recording of this session by tomorrow. Okay, so for the new people, I hope you understood most of it. Go through the previous recordings as well. Okay, and casting video, you have it. I have given it to the newspaper people. They have the casting video. I'll ask them to upload it as soon as possible. I've given all the videos to them. I'll ask them tomorrow. Okay, so till next time, have a good day. Keep working on the things you are weak on, and I'll ask them. I'll tell them to upload as soon as possible. Okay, and keep using the forum to learn. Put some good questions on it for your friends and for you to, and for your doubts. Okay, so till next time, have a good day. Bye bye. Good night.